Hello, everyone. I'd like to welcome you all to this presentation. I'd like to begin by thanking the organizers to include me. And I wish, I should say, that we could have met in person, but that was not meant to be. But the good news, I guess, if there is any, is that some kind of vaccine is around the corner. And and hopefully it becomes available to all of us everywhere soon. So let's get started with a very brief introduction. My name is Narendra Mohan. So Narendra is a name that you probably all familiar with, but my Americanized name is Ned, and that happened long ago. And if it was today, it may have been a little different. But anyway, that's the name I'm stuck with, Ned Mohan. So let's get started with that brief introduction of mine that I'm at the University of Minnesota, and this is my 44th year of teaching. So what I would like to share with you are some of the slides that I have prepared. And, I would say that probably you are all very familiar with them, uh, but let's just sort of review them in a way. So let me get started here, and I'm using Zoom, and I hope I'm able to do it properly, and I'll also hope that I'm being recorded here. All right, so the topic of the presentation that I have is Power Engineering Education in the Age of Climate Crisis, a holistic view. What you see here is a kind of a shot, of our campus. The river Mississippi flows right through it. So it's a beautiful campus, at least in summertime. In wintertime, it's quite a bit covered with snow. And then at the bottom, you see my email address. In case you want to reach me, please feel free to do so. All right, so with that little bit of background, let's go to the next slide here. I always start my lectures by showing this slide here that it kind of puts humility into context that, you know, there is nothing new actually. The greatest accomplishment of 20th century science has been the discovery of human ignorance. So that's Dr. Lewis Thomas. He was a physician and also a medical writer. And similarly, this is philosopher emperor on the left. He's talking about everything we hear is an opinion, not a fact. Everything we see is a perspective, not the truth. Well, I would say there's an exception. Climate crisis is not an opinion. If you believe in science, it's a fact. All right, so let's leave it at that. And then, this electricity is basically a basic human right. Okay, I grew up in Jabalpur, which is in Madhya Pradesh, and I used to travel with my father to small towns where there was no electricity. Okay, so it was then, and I didn't realize how serious it was. But today, now that we are used to electricity, I think it's basically a human right issue that, so many people, as you see in the slide, according to the United Nations, 1.3 billion people are without any access to electricity. So, this link that you see at the bottom of this slide is a presentation by Rajiv Shah. Rajiv Shah is the president of the Rockefeller Foundation, okay? And he talks about energy poverty, what it means, for example, in Bihar, where he traveled to. And he has teamed up with Tata, and you're all familiar with Tata Electric, about $1.5 billion to $1 billion project to bring electricity to villages using photovoltaic. So I really urge you to take a look at this link a first half an hour of it, where he is talking. All right. So climate change. Well, there's not much doubt at this stage that climate change is happening, and it's basically happening because of our activities. So we had organized a workshop in 2017 where Dr. Gavin Schmidt, who's the director of a NASA institute, and this NASA institute is called Institute for Space Studies, okay? Institute for Space Studies. So he is a modeler and a predictor, okay? And he gave a presentation very convincing, as convincing as I have ever seen. And he talks about how, climate has changed from pre-industrial age, uh, about 1 degree centigrade, which is about 2 degrees Fahrenheit, okay? And he talks about that it took only uh, 4 degrees centigrade to bring about ice age. So we have already gone roughly 1/4 of ice age in the other direction. And you have heard of this Paris Accord of 2015 and how it will limit temperature rise to 2 degrees centigrade, perhaps 1.5 degrees centigrade. So, all these things are very important to at least delay the catastrophes ahead, if not totally avert them, because what we have already done to the planet. All right, so this is what, I'll go back to the previous slide. I'll urge you to look at this WIP link here, his half an hour presentation. You can download from this link. All right, so he talks about that in, in the worst scenario, if we keep doing what we are doing, the picture that you see is on the right lower hand corner, where our climate would ultimately become that of Venus, and life as we know it would be impossible. And aggressive mitigation, he has totally ruled out because that should have begun yesterday, and even now there is no accord as such between countries. So he just hopeful is the serious mitigation, which you see on the middle, on the upper side. And even there, he says that there will be portions of the globe where temperatures would reach as high as 4 degrees centigrade, which he said is a full ice age unit in the opposite direction. So these are pretty scary predictions, and these are for year 2100. But not that everything would be rosy until December 30th of 2099, and just certainly things would change in year 2100. Things would, if we don't do something, things would slide towards that catastrophic event or events. All right, so what do we have? Well, we are technology people, and technology is essential. And there we have basically two options to reduce our carbon emission. One is to use wind, and the other is to use solar. So here, our National Renewable Energy Lab has done some life cycle analysis, and they tell us that compared to coal, which produces 1,000 grams, 1 kilogram of CO2 equivalent for every kilowatt hour of generation of electricity. Okay, so compared to that, wind is 10 grams, which is 100 times cleaner, and then solar is 40 grams, so that is 25 times cleaner. So this is life cycle analysis from cradle to grave type of things, right? So at least they have made an attempt to include everything. All right, so now the good news is that the cost of these renewables has been going down. So here is a chart that is produced by this Lazard Associates. That's a very often quoted website, at least in the United States. And so whatever I'm presenting to you is sort of US centric, because I don't have much information on a worldwide basis. So these slides that I have put together are, pulling information out of US sources. So you see here that coal and gas, they are, 52 and $65 per megawatt hour, whereas solar and wind are quite a bit cheaper, 32 for wind and 43 for solar, right? So that is why a lot of utilities, not that they are all that interested, well, they may be interested, I shouldn't say that. They're interested in the climate and the environment because it will affect us all. But they are, in the short run, interested in the bottom line. Okay, so if solar and wind are cheaper, then why not use coal? Why not use them as compared to gas and coal? But rooftop solar, putting solar panels on the roof, they are still very expensive. So that's an area where a lot of research can be done to bring down the cost. Okay, so that's a good news. And so the answer is that first of all, we should shift all our energy use, wherever we use energy, to shift it to electricity as much as possible, and then generate that electricity from renewables like wind and solar. All right. And then conservation, which is kind of a missing piece. We don't often think about conservation, at least in the US. And that is very important, because any electricity we don't use is not going to produce any greenhouse gas. And then we have to develop a sustainability mindset wherever we can reduce our energy, electricity consumption. We should do that. But at the end, we also have to realize that the science alone cannot stop global warming. Our human attitudes must change. Okay, but so what technology we are talking about here is essential, is totally essential, but not sufficient. These human attitudes must change. Okay, so here is uh, a picture that I took from this book by Varun Sivaram, and there's a web link given here. That book, where is it? I had it here somewhere in front of you. I don't see it. So I just found it here. So if I could put it in front of my face, you can see this book, I hope. It's uh, called Taming the Sun. Taming the Sun. Okay, so he's really, uh, a tremendous young man uh, who has done so much in his, in such a short period. And what he shows at the left here is value versus cost for installed capacity. So as the penetration of these renewables increases, which is plotted on the horizontal axis, you see what's happening to cost and value. Okay, and you can see that cost is declining, shown in red, and the value is declining, also shown in blue. And you can see that there is a crossover at a certain installed capacity. And why is value decreasing as the installed capacity increases? Well, the reason is that, as you well know, that these renewables are variable, they're intermittent. The wind always doesn't blow and sun always doesn't shine. Okay, so because of that reason, and the batteries are still expensive, and therefore the value goes down as the installed capacity increases. And you can see the crossover point on the slide on the left. But if you reduce the cost, okay, of these renewables, and that's where the challenge for us is, to continuously keep reducing the cost of these renewables. So if we reduce the cost, new cost is shown in solid red line in the middle picture. And you can see that then the crossover happens at a larger installed capacity. But then the slide on the right, a picture on the right shows that if we keep on decreasing the cost as well as some systemic innovations that he talks about, and you can look at the meaning of that, then the crossover may never happen. Okay, you can keep installing more and more renewables. Okay, so that's what we see on the right here. All right, so we have a long way to go. Okay, so here are the figures for the electricity generated in the United States in 2018. And in 2019, you can look it up going to this link shown below. And what is showing us is that wind and solar were a very small part of this total electricity that was generated in the United States. So photovoltaic was only 1.5%, and the wind was only 6.6%. So if you look at it on a global basis, and you'll see that it's even smaller on a global basis. Okay, so we have a long way to go, but so we should get started on this. And in doing so, we should really take a holistic view, okay? Because the world is not compartmentalized into power electronics, electric drives, and control. All these things are, kind of taken together to build up a system. And so we should look at it in a holistic way, how we generate electricity, how we transmit that electricity, and how ultimately it's used in the end. So, obviously we should, generate it using renewables. We should transmit it as efficiently as possible, and then of course conserve. And then we should also look at applications and use transportation. Okay, we'll talk about transportation. Okay, and defense, that's important, as well as industrial competitiveness, like automation, robotics, advanced manufacturing, and so on. Okay, so take a holistic view. Okay, so for wind, we know how the system looks like. We have these towers, and in the nacelle, at the top of these towers, we have the blades, we have a gearbox, we have a generator, and that generator runs at a variable speed depending upon the wind speed and how fast these blades are rotating. And then this variable frequency, variable amplitude voltage, and current, that power comes down the cables, and this may be 100 meters tall tower, and at the base of these towers is a power electronics converter, which converts a variable frequency, variable amplitude AC to, let's say, 690 volts, and 60 hertz that we use in this country, voltages and currents. And then at the base of the tower, there's another transformer which boosts us up to 34.5 kV. And so that has become a de facto collection grid voltage at which hundreds of wind turbines in a wind plant may be connected. Then all that power is aggregated, and there's another transformer there that transfers 34.5 kV and boosts us up to 161 kV. Okay, and then it's transmitted over transmission lines. Okay, so you can see that here we are using, of course, mechanical concepts, but then also electric machines and drives. That is in the machine is in the nacelle above our ground, and then you have power electronics converter, then you have transformers and the transmission line. So they all make up this whole system, including, and then control. Control is very important, and also how these turbines should operate under fault conditions, so-called zero voltage right through. Okay, so all those things are sort of all in one system. Okay, so that's why we need to take a comprehensive look on this education. Okay, and same thing with solar. You have a picture of this Topaz solar plant in Southern California, It's a 550 megawatt plant spread over a large area. And so in the bottom left, you see the sort of a schematic of how power is collected from all these photovoltaic panels, how it's converted to AC through a power electronics converter. Then there are transformers to haul it away to wherever the loads may be. But also, I mentioned to you about rooftop solar. So that's where there's a lot of potential. This National Renewable Energy Lab is telling us that 40% of our electricity we can generate through rooftop solar, because the solar roofs, the roofs are already there. We just have to put up these solar panels. But the cost of those installations are still pretty high. Okay, so hopefully, uh, as time goes by, those costs come down. All right. So we also need storage, because we talked about how these solar and wind resources are variable. So here is a slide in green. You see what wind is doing as a function of time, but these red dots you see, uh, they indicate what wind was generating when the demand was the highest on the on the system. Okay, so they are kind of they are not correlated at all, right? Because wind was producing very little when the demand was highest. Okay, not always the case. And if you have diversity, you can reduce this picture, this anomaly. So but it clearly indicates the need for storage. Okay, so that is kind of a missing link at this time. And but a lot of research is going on in making these batteries cheaper and more efficient. Okay, and on the right here, you see what we call a duck curve. So this is kind of what is happening in California. And what you see here is the load demand on the utility as a function of time in a given day. And you can see that when the sun is shining and photovoltaics is producing a lot of power, the demand on the utility system goes down around the noon hour. And then as evening approaches, people are getting home, turning on their appliances, and the sun is going down. So therefore, the demand on the utility system ramps up. Okay, demand from the utility system ramps up. And you can see there's a tremendous ramp that these utilities generators need to have to meet that demand. Okay, so that's again a problem that could be somewhat reduced by having storage. Then in terms of transmission, there has been a talk of this high voltage DC grid. So that's still in the planning, and who knows whether it'll ever come about. But if it does, what it'll do is kind of introduce diversity. So throughout the entire country, for example, it'll take the resources from wind and solar and put it on this grid. And so some places where sun is not shining, in other places it may be shining, and similarly about wind. So it can make use of that diversity. All right. So again, I like to point out one part which is often overlooked is the role of electric machines and drives, okay, for this type of application. So, we know that we need these drives for generating power from wind plants, wind turbines, but we also need them for electric transportation, right? And we'll talk about transportation. So those are the two major applications that we can think about. And talking about transportation in the United States, the carbon footprint of transportation has exceeded that of the electric power sector. And this crossover happened in somewhere in 2016. So transportation, which is, by and large, almost by using gasoline, petroleum, so that has to change to electric, okay? If you're going to get rid of this greenhouse gas emissions in transportation, okay? So, these electric cars are coming, and still a very little penetration in the United States. And so you can see a charger here, and we had played a role. It didn't go too far because what we had developed was for charging of electric vehicles that General Motors was producing at that time in mid 1990s. So there's something called Minnesota rectifier, which our university had patented. And it was used to charge a fleet of cars, not individual electric vehicles, but a fleet of cars. But then General Motors, they were leasing these electric cars called EV1, and they thought that there was no money to be made. So they took back all those cars, and they were shredded in California desert. So there's a movie called Who Killed the Electric Car? So if you get some time, please take a look here. So the unfortunate part, and I think it's happening probably everywhere, the enrollments in the electrical engineering programs are dropping, okay? Whereas they are increasing in these trendy areas like, they're important too, like AI and machine learning and big data. But these electrical engineering programs like what we are talking about here, they are equally important. So here is the history of electric energy curriculum and how it was in the decline, where these courses had not changed over a long period of time. And so that needs to change. So I'll not read through all the bullets here, but now power engineering is seen as critical to growth and sustainability. So we need to rethink the curriculum, okay? So I'm sorry, I went the other way. So the proposed approach we have is first to design a pipeline course from where, by which we can entice, attract students from high school to come to in this curriculum, and then give them very solid information by few carefully designed undergraduate courses, and then have graduate courses that may be shared with colleagues across the country, and they could be online. So I'd like to talk to you about all of them, okay? So this is a pipeline course we have developed. Last time we taught in fall of 2019, we had 111 students, okay? So, it could be a very popular course. It could be taught on a university-wide basis, because in this course, you don't even need to have a physics background, high school physics background. Whatever physics is needed, we teach it. So here's a website here, and I'll urge you to take a look at the structure of this course. So we have very high hopes going forward with this course here. So like I mentioned to you, this course can also be taught in high schools. And if high school students take this course, they get university credits in addition to satisfying their high school requirements, okay? So it's called dual credit concurrent enrollment program, okay? So right now we are teaching this in only 5 high schools in Minnesota, but there are, about 500 high schools, and maybe 20 in Minnesota alone. And if you multiply that 50, Minnesota being an average size state, there could be 2,500 high schools. I don't even know how many high schools there may be in India, for example. Lot more. Okay. So we really need to look at this electric power engineering curriculum in a holistic manner. And this, when we say power, this includes power systems, power electronics, electric machines and drives, as well as controls. So what we did at our university, that of course we have core courses in the middle, that all students, whether they're going into power, all students have to take them, like circuits and some basic controls. But then we designed very carefully 3 courses, one in power electronics, one in electric drives, and one in power systems. And these are standalone courses, and students can take any combination of those. And that allowed us to have these complementary courses before they graduate. Because our feeling was that undergraduate is not necessarily for specializing in any one particular area. Some focus, but not totally specializing, but rather to have a broad-based education. So when they graduate, they can choose to go in whatever field they may wish to. But still, you have to have a little bit of emphasis in one particular area. So in this case, the area we are talking about is power. Okay. So this slide, I kind of shaded it out, but it shows that we had, our enrollments in these courses almost tripled. Because of privacy, I shaded it out, but from 15 or 20, it went as high as 90 students in one semester. So to accomplish that, our group has been writing textbooks. On the left, you see this uh, power electronics textbook. It was, I think this date may be wrong. It was, I think, 2003. So this number here, maybe I can change it right here. I think this number was 2003 when the 3rd edition came out. And then there are some subsequent books which are basically tailored for undergraduate courses. One is on power electronics, other one is electric machines and drives, and the third one is on advanced electric drives, which is for a graduate level course. So what my postdoc Siddharth Raju and I did was to take all these 3 books and combine them into a sort of a one single book, which just came out in August of this year. And this is on analysis and control of electric drives. Okay, so the unique aspect of this is that it has simulations in a platform that was developed here called Workbench. And if you simulate using that platform, then you can seamlessly control a hardware laboratory. So I'll talk about it a little bit in a minute. Okay. So we have this website called CUSP, and the URL for that website is at the bottom. And so all the material that we're developing, we're uploading onto this website, and it's totally free to download for anybody. Okay. You don't even have to become a member. But 235 US universities have become members. I don't think at the moment anyway, there is any benefit to becoming a member, because all the material that we have can be downloaded by anyone without becoming a member. But we are hoping that at some point through these members, we have some further development that we can upload to this CUSP website. All right, so we have developed 17 senior and graduate level courses. And you can see the breakdown here in power systems, power electronics, electric machines and drives, and renewable energy. Okay, so we have been using this material quite a bit in the courses that we are teaching here at our university. And then I'd like to talk to you about, in the time remaining, about these hardware labs that we have developed. So this development started almost 15 to 20 years ago, and approximately, actually, we know these numbers pretty well. Not about 109 US universities have acquired these hardware laboratories. But they have been getting old, right? They were developed 15 years ago. So if components break down, it's very hard to find these legacy components So we have been very fortunate that through a 4-year grant from our Office of Naval Research, which is a part of the US Navy, we are developing new laboratories which are wide bandgap based. They're extremely low cost compared to what we had in the past, and they are digitally controlled. So here is a picture of a drives laboratory, electric drives, and so this, before going to the lab, I should say that we could use these materials that we have developed for online master's degree program. And here is a simulation platform picture, and then the hardware that can be controlled if you do your simulations in this platform that which we have developed. Is very much like MATLAB Simulink, but it's totally free. Okay, MATLAB Simulink is not free. Okay, whereas this is totally free. And if you simulate your system using this platform, then controlling these laboratories in the these hardware laboratories is seamless. Okay, so a little bit of description of what this platform looks like, and as you can see, not all that different from MATLAB Simulink if you're used to it. And here is the setup for induction motor vector control. So not only you can control and characterize these induction machines like in an undergraduate course, but you can also use them for vector control that is often taught in a graduate course. Okay. And so what this simulation would look like for this vector control, and the results would be like, let's say you want to change the speed from one level to another, how you can go to it very fast. And that can only be done if you're using vector control. Okay. And then some results here I'll skip over. All right. And then also for permanent magnet synchronous machines. Okay. So the whole kit here is very low cost, and that is what's shown in this slide here. Okay, so this was the previously used system we were using, and the cost comes out to be $40,000 for non-academic and about $20,000 for academic purposes. But these laboratories that we have designed and we have been using them now are extremely low cost. Perhaps a factor of 5 they are, maybe more. Look at here, the total cost here is $3,000, right? And so compared to $20,000 in the previous setup, this is about 7 times cheaper here. And so this is what an electric drives kit looks like. It comes in this box. It has DC motors, and then it has a synchronous permanent magnet synchronous machine, an induction machine here, and then and this inverter board, which is described here in more detail. So it uses a very low cost TI DSP, which is on board over here. Okay, and so this has been a tremendous success for us, and you can see the experiments that can be conducted in the basic drives lab and then advanced power drives lab. So before that, using the old setup, we were never able to do these advanced experiments like vector control. But all those are now possible using this drives laboratory we have. Similarly, we have a laboratory for, and this is again using wide bandgap devices and digitally controlled, and we can control this laboratory to do all these experiments that are listed here. Okay, and that was again not possible with the laboratory. Only probably 1/3 of these could have been done in our previous laboratory in power electronics, but now they are all possible here. And then we have dreams of extending it for power system emulation. Okay, so you see here that each card can emulate, I should say, emulate, because this is happening in real time. It can emulate a PV system on the left and it can emulate a grid on the right and interconnect the two. So in a microgrid, for example, we can emulate 5 nodes, some of them generating power and some of them consuming power, right? And only the losses need to come from a DC power supply. So this is at a pretty low voltage of 40 volts. We are just trying to make students understand the concepts, right? So 40 volts, so very low cost, but it gives all the concepts that needed to be explained, right? So here are the list of experiments. Because of the time, I'll not read through them, okay? And so the other beautiful picture, unique point, I should say, of these laboratories is that they can be controlled remotely, okay? Remote control, okay? So here I made up this picture like a cartoon, okay? So let's say you have a power electronics laboratory and you just need one setup, okay? Usually in a laboratory, you have 5 or 10 setups, right? We don't need that. We just need one setup, okay? And because they are digitally controlled, they can be controlled through the internet, okay? So let's say in week number 3, you have an experiment on flyback converters. When you can set up this thing for a flyback converter, and students can then have a timesheet where they sign up for a 2-hour slot. So you see here the student on the upper left, he or she has signed up for a time slot from 2 a.m. to 4 a.m. Okay, I know students work 24/7, right? So no, I'm just joking, but any time of the day or evening or night, a student can sign up for this two hours time slot, and then other students can sign up for other time slots. And then every week, the instructor or the teaching assistant can change the experiment from flyback converters to boost converter or whatever, right? So the point I'm trying to make is that it becomes cheaper by another factor of 5 or 10, because for 30 students, let's say, you just need one setup. Okay, so that's so imagine that for $2,300, you can set up the entire laboratory course. Okay. So also, this postdoc Siddharth Raju, he has developed this general purpose prototyping platform, which is very low cost, and it can be used for research purposes. So we are using it in many research projects that we have. I don't have time to talk about those, but they can all be utilizing these. And these laboratories could also be used for, doing some research projects at a very low power and low voltage level before they go into, before students build their prototype at high voltages and higher power. Okay, so the contact information of Dr. Siddharth Raju can be found on this website that I have listed here. Let me just click on here just to show you what this website looks like. And you just go to this website, and it has product information. So it's really a University of Minnesota startup, okay? And just for the record, I have zero financial interest in this startup here. My role really is to disseminate this information that is available for you to use, okay? So let me go back to these slides here. So I must acknowledge this grant we have from Office of Naval Research, which has allowed all these things for us to happen. And the goal of this grant was really dissemination, not just to make this development happen at University of Minnesota, but promote it nationwide, in fact, worldwide. There's no restriction, okay? So I'm coming to the last slide here, that, we are on this, we are a spec on a spec, which is circling around this middle-aged star we call the sun. And there are 200 billion such stars in our galaxy, the Milky Way. And scientists are telling us, observational astronomy is telling us that there may be over a trillion galaxies. But anyway, the bottom line is that this is the planet we have, and there is no planet B, like they say, plan B, right? There is no planet B. And this Professor Carl Sagan says there is no hint that help will come from elsewhere to save us from ourselves. So true, so true. So thank you very much. I hope uh, I did some justice to this presentation. Any comments or questions you have, I'll be very glad to entertain them. So once again, thank you very much. Bye-bye.